Hello and welcome back. In the following, we want to use convolutional neural networks to identify and classify damage site-induced phase steals. So before we start, we need to discuss the problem setting a bit more and think about what we want to do and why we want to do it and how we can approach this problem. So modern steals are used in a wide range of applications, from automotive sectors to construction and many others. And one of the types of steals with high relevance to the industrial applications is the so-called dual-phase steal that has a temperature of 800 megapascal, and this is fairly ubiquitous in many application areas, and this is known as the DP800 steels. And the name originates from the microstructure of the steel and consists of two phases: a hard martensite phase and a softer ferrite matrix in which these harder martensite ions are embedded. A lot of research, both in university but also in companies, is focused on how to improve this and similar kind of steels. And in order to be able to do that, it is important to understand how these materials behave if we subject it to stress. For example, it's particularly important to understand what kind of damage types occur during deformation and how these kind of damage sites evolve under additional strain. Now here we only focus on the initial stages of damage, the creation of deformation-induced voids, and then we have a number of those that we can discriminate between. There are inclusions, and these are much larger damage sites. They typically form during the production process. Essentially, there's a foreign object or an impurity that gets embedded into the steel when it is produced, and then during the preparation of the sample, when we look at it with the electron microscope, this particle then often falls out and we have a larger hole remaining. So this is a type of damage that's mainly related to the production process. But what we are very interested in is in the ductile damage, the damage that occurs if we subject this steel to mechanical stress. And there we have three main prevalent types: the martensite cracker. Remember that we said that the steel consists of the martensite phase and the ferrite phase, and the martensite phase forms these islands, and they are much harder, so they can crack. So this is one way in which damage can occur. And we have what's called interface decohesion, like if you can imagine that the martensite and the ferrite phase, when they come into contact, and if you then pull at the sample, that they can come apart at this interface between them. This is why it's called interface decohesion. It's also what we can call notch effect or resolution limit, and this was essentially introduced to account for damages that we see that there is a damage or there will be a damage soon. It's just nucleating, but it's so small that we cannot really tell what kind of damage it will be. If you want to learn more, there's an application, large error resolution characterization classification of damage mechanism dual phase steal using deep learning and the successor to those. And if we want to do this now ourselves, we have to realize that all types of damage have in common that they appear as a dark region in the sample. And that is because the surface of the sample is disturbed. So, for example, we have crack, or we have this interface decohesion, or even the occlusion. And when we put the sample into the electron microscope, the electron beam cannot go into this crack, for example, shall we say, and then get out and reach the detector, and this is why it remains dark. There are also some imaging artifacts, in particular shadows. You can imagine that even if you prepare your sample very well, it will still have a very small but noticeable 3D structure. And so depending on how the electron beam hits the sample, you may have the situation that some of this 3D structure of the steel sample creates a little bit of shadow, just because of the geometry of how the electron beam hits the sample and then gets reflected to the detector. And that also leads to dark regions. We have said before that dark regions typically indicate damage because the electron beam is trapped, but they also are related to these artifacts. This becomes important if we want to analyze the data and also identify what is an actual damage and what is an artifact. And this is particularly important because these damage sites occur, though relatively infrequently, but because it's a stochastic process, we don't want to look at 1 or 2 damage sites, we want to look at large numbers, hundreds or typically thousands more than we can do by hand. And this is also why we want to use machine learning. Typically what we do is we take a large-scale image, a panoramic image, at very high resolution in our electron microscope, and then look at all the individual damage sites and try to classify what they do. And this is why you cannot do this by hand, because you first need to identify all of these thousands of damage sites and then classify what each damage site is. So the way we do this is we create the positions of potential damage site candidates, set a threshold, so everything that's dark so has a low intensity value, and then we can run a clustering algorithm to identify which of these damage sites should be considered further, because if there's only 1 or 2 black pixels, we don't want to identify this as damage. And then we use 2 different neural networks. First, the neural networks to identify the conclusions versus all the other types of damages, and then second neural network to identify the remaining types of damages. And these neural networks are trained using a large data set of manually labeled images where experts have spent a lot of time creating these labels for each image and curate the data set. And the data set are such that for training, we always place the damage site in the middle and then have an image around it. So before we start to get on with the technical side, consider the following. Why do we do this 2-step approach? For example, there are other methods like YOLO that combine the location and identification. Why do we need the clustering approach? Which clustering algorithm would you use? And why do we use 2 networks instead of just 1? So why do we take this 2-step approach? One of the aspects of scientific work is that we're also able to quantify uncertainty. So 1-step approach like YOLO requires that we first select and label a set of training data manually, and typically we use some GUI to draw a rectangle or a large image that contains the object of interest. And this is quite prone to biases. For example, how would you as a user select those damage sets that we use for training? What does a human do? What do they miss? And how does that vary from human to user, from human to human? You can imagine if you gave the same task to 5 people, they would come up with different selections because they might not select the same spot. So this is a variation that you at least need to understand. Also the box size, and if you leave that up to the human, then different humans will choose different box sizes. And again, this is a variation that you would need to understand if this causes an issue. So essentially we use this approach of first identifying potential sites with a threshold, and then clustering, and then using a fixed image size to avoid all of these potential biases. And then, why do we need the clustering approach? Well, the damage sites are found by setting the threshold, as we said, to identify the dark region. But we have maybe individual small pixels due to random noise or just because they just happen to fall below the threshold and so on. So we want to have at least a few pixels grouped together, and this is what clustering do this for us. Which clustering is suitable? Because we don't know how many clusters we have and what the shape is, we will use dbScan from the scikit-learn library. And why do we use 2 networks instead of 1? Well, the inclusions are very different, both from the material science perspective, from the way they are formed, like they are the production impurities, and they are distinctly different from the ductile damage. So it makes sense to split those, even if it could be in one network, and then it depends on the exact networks you choose if this brings now a benefit or not. For the approach that we will choose here, we have two networks, one to identify just inclusions and one for the ductile damage.